Welcome to the greenhouse effect lesson. We're going to talk about what greenhouse gases do in the atmosphere and how they influence energy flows. In particular, we'll have a look at the basic molecular structures of some different gases to see if they yield any clues to which gases are greenhouse gases and which are not. Then we'll talk about inflows and outflows of energy to and from greenhouse gas molecules. Greenhouse gases don't just absorb energy, they also emit energy. And the sum of all the greenhouse gas actions together helps warm Earth to temperatures higher than it would be without greenhouse gases in the atmosphere. The greenhouse effect makes Earth comfortably habitable. We'll start with a little context. The greenhouse effect is another one of those places in Earth's climate system where we have opportunities to perturb flows of energy. We've been perturbing energy flows via the greenhouse effect pathway pretty well so far. And the way we do it is by increasing the inflow of carbon dioxide and other greenhouse gases to the atmosphere so that their stocks go up. We've seen this plot before. It's the increase in atmospheric carbon dioxide since the late 1950s. These particular measurements were made at Mauna Loa Observatory in Hawaii, which is a good place because it's fairly high altitude and it's far enough away from local CO2 sources that might cause problems with the measurements. Also, Earth's atmosphere is generally well mixed with respect to CO2, and the long-term upward trend in the Mauna Loa data is a good indication of what's happening globally. And what's been happening is that inflows from burning fossil fuels, land use changes, and cement making have exceeded outflows to the oceans and plants and soils on land. So the CO2 stock goes up. As we think about mitigation options going forward, actions that could bring the concentration of greenhouse gases back down would help counteract these historical greenhouse perturbations. Here's that diagram of Earth's energy budget again. The parts of most interest to us in this lesson are those involved in the greenhouse effect, which is all the stuff on the right side of the diagram. It's the stuff like surface radiation, the stuff absorbed by the atmosphere, emitted by the atmosphere, greenhouse gases, back radiation, absorbed by the surface, all of those arrows. We'll start with a question. What would you expect to happen to the surface radiation flow if greenhouse gases increased? If greenhouse gases increased, the energy emitted by greenhouse gases would increase, and some of that energy would go back toward Earth's surface to be reabsorbed. So we'd expect the back radiation values shown on this image to increase as greenhouse gases increase. So that's making the total inflows of energy to Earth's surface go up. To balance that extra inflow, we'd need additional outflow. Of course, some of the outflow could be made up by latent heat transfer or thermals, which we talked about before, but likely some of the extra outflow would be via surface radiation. So that would go up, associated with an increase in temperature. And try this review question. Here are the distributions of radiation emitted by the sun and by Earth. The types of radiation each emits depends on their temperature, which we saw earlier, and since the sun is hot, it emits ultraviolet, visible, and infrared radiation with a peak wavelength in the visible. The Earth is much cooler than the sun, and therefore it emits radiation in the infrared, which we can't see. What's closest to your idea about the type of radiation with which greenhouse gases interact? Here it is on the energy budget diagram again. The radiation with which greenhouse gases interact is the long-wave radiation coming from Earth's surface. It's not short-wave radiation coming in from the sun. The greenhouse effect is all about long-wave infrared radiation. Let's talk a bit now about molecular structure of gases. What makes a good greenhouse gas? Well, a good greenhouse gas is one that can absorb and emit radiation within the same range of infrared wavelengths as are emitted by Earth's surface. What's your initial impression of these gases? The circles represent atoms and the lines are bonds between the atoms. Which ones might be good? One thing to consider is what kinds of vibrational motions a gas molecule can do. If a gas molecule can vibrate in a way that creates small asymmetrical charge imbalances or a little dipole, which means that part of the molecule gets a slightly more positive charge and another part of the molecule gets a slightly more negative charge, then it can absorb and emit infrared radiation. This is even though the molecules are electrically neutral overall. Molecules with two atoms, both of the same element, can stretch. So their atoms move toward and away from one another, but they can only stretch symmetrically. With symmetrical stretching, the molecule's center of mass stays in the same place, the center of charge also stays in the same place, and no localized charge imbalances happen. This type of stretching does not interact with infrared radiation. So molecules with two atoms of the same element are not greenhouse gases. In our atmosphere, the most common gases are N2 and O2, two atom molecules. These are not greenhouse gases. Molecules with three atoms can also stretch symmetrically. And again, this type of stretching doesn't interact with infrared radiation. However, molecules with three atoms can also do other things. They can vibrate by stretching asymmetrically, and they can bend, also an asymmetrical movement. This type of asymmetrical motion does create localized charge imbalances, and these modes of vibration do interact with infrared radiation. The fact that greenhouse gases can have more than one bending, stretching, or vibrational mode means that a single gas is capable of absorbing and emitting infrared radiation at different wavelengths. The particular wavelengths each gas likes are very specific to the chemical structure of the gas and which wavelengths of infrared radiation match the frequencies at which the molecule vibrates. A useful analogy is like when you push someone on a swing. If you add energy by pushing at the right frequency, the person will swing higher. If you push at the wrong time, you'll damp the swing's motion. Greenhouse gas molecules only vibrate when they get a chance encounter with energy of the right frequency. Here are examples of the two most important greenhouse gases, water vapor and carbon dioxide, and a couple of ways in which each of them can stretch and bend when they absorb and emit infrared radiation. With water vapor, the hydrogen atoms can stretch toward and away from the oxygen, or the angle between the arms of the molecule can change a bit as the molecule bends back and forth. CO2 can manage an asymmetrical stretch if the central carbon atom alternately gets a bit closer to one of the oxygens, then a bit closer to the other. Or it can bend a little back and forth, forming a slight V shape. These are just a few examples. Let's take a more detailed look at what's happening in the atmosphere. After a greenhouse gas molecule absorbs infrared energy coming from Earth's surface, what happens next? What would happen if you just kept eating, which is gaining energy, but you never lost any energy? We lose energy, for example, as heat radiating from our bodies. If you did that, you'd quickly have a serious imbalance. Greenhouse gases have to get rid of the energy they absorb too, so they emit or radiate the infrared energy away again. They're also constantly undergoing collisions with other gas molecules, gaining and losing energy that way. But about emission, the greenhouse gases emit radiation in random directions at all sorts of different angles. Some of the re-emitted radiation heads upward, some heads downward, some sideways. It could go in any direction. Some of the re-emitted radiation then encounters another greenhouse gas molecule, which in turn absorbs, then re-emits the energy, again in a random direction. So after potentially lots of encounters with greenhouse gas molecules, some of the radiation makes its way back to Earth's surface, where it's absorbed. Since Earth's surface is absorbing radiation from the sun and radiation from greenhouse gases, the surface warms up until it can radiate the sum of those two sources back to the atmosphere, as we've seen. And in order for the whole planet to be in balance, the radiation leaving to outer space has to match the radiation coming in the top of the atmosphere from the sun, or else the planet will warm or cool. The main point of this figure is that energy may be absorbed and re-emitted by greenhouse gases in the atmosphere many times before it either leaves to outer space or gets reabsorbed by Earth's surface for another round. Notice that there are more greenhouse gas molecules nearer the surface, just like all the gases that are well mixed in the atmosphere. The atmosphere gets thinner higher up, so the higher up the energy makes it, the more likely it is to escape to space, if it happens to get emitted in the right direction. Note also that one pathway here represents infrared radiation of the special infrared wavelengths that don't interact with any atmospheric gases. This radiation proceeds directly back to space. So again, The greenhouse gases are those that absorb and re-emit infrared radiation coming from Earth's surface. And we mentioned that greenhouse gases can have more than one mode of vibration and can therefore absorb and emit infrared radiation at different particular wavelengths. This figure is a good way to look at the wavelengths each gas can interact with. The upper panel shows the emission spectra for the Sun and Earth, which we've seen before. Those are the smooth curves. And the lower panels show the wavelengths at which different gases absorb and re-emit. There are a bunch of little panels, each for a different gas. The vertical axis for each of these lower plots is absorption, with high absorption being up and low absorption being down. Based on these plots, which gas do you think would be the best greenhouse gas? That is, absorbs and emits the most radiation in the wavelength range of energy given off by Earth. Water vapor is a great greenhouse gas. It has a bunch of different vibrational modes, and it's capable of absorbing and re-emitting radiation at a lot of different wavelengths. Carbon dioxide has one major absorption band centered around 15 micrometers wavelength, which is nicely situated toward the middle of Earth's emission spectrum. So there are lots of those 15 micrometer photons available. Ozone primarily absorbs incoming ultraviolet radiation from the sun. You can see that on the far left side of the plot. But it also has an absorption band out there in the infrared. So at that infrared wavelength, ozone behaves as a greenhouse gas. And the remaining two gases, methane and nitrous oxide, have very particular tastes in infrared radiation and narrow absorption bands. The last thing to notice about this plot is that blue part of the upper panel. This represents those wavelengths of infrared radiation emitted by Earth that none of the greenhouse gases like very much. So those wavelengths are the ones that pass straight through the atmosphere directly to space. That's the 40 watts per meter squared we saw on the Earth's radiation budget diagram. So here are some key points about the greenhouse effect. The greenhouse effect involves infrared radiation, the stuff emitted by Earth's surface, not incoming solar radiation. The greenhouse gases have chemical structures such that they can wiggle and vibrate and absorb and re-emit infrared radiation. They re-emit it in random directions, which means the energy sticks around in Earth's climate system longer, and Earth's surface absorbs more total energy, warming it up until it's warm enough to emit the same amount of energy back, equal to the total it absorbs. Greenhouse gas concentrations in the atmosphere have been increasing, which increases the magnitude of the greenhouse effect.